So what we have seen till now is that when you cascade two linear operators, you get a linear operator, and we saw how to calculate the cascaded linear operator. Now think about this. Just like if you cascade two linear operators, you get a linear operator. What will happen if you cascade two shift invariant operators? Right? Think about it. You have a shift invariant operator. I'm not talking about linearity right now. A shift invariant operator and another shift invariant operator. So what happens to the cascade? What happens? You get a shift invariant operator. Now, how do you get a shift invariant operator? If the first signal is shifted by a certain amount, that means that the output of the first operation will be shifted by a certain amount, which means that the output of the second operation will be shifted by the same amount, which means that if you cascade two shift invariant operations or two shift invariant functions, you get a shift invariant function. If you cascade two linear operators, you get a linear operator. If you cascade two shift invariant operations, you get a shift invariant operation. So what happens when you cascade two linear shift invariant operations? So if you cascade two linear and shift invariant operations, functions, what you will get evidently is a linear and shift invariant function. What that means is that if you cascade two convolutions, you get a convolution, right? Think about that. You have some convolution, you have some other convolution, right? Let's say this convolution is some convolution with a spreading rule F. You have another convolution with a spreading rule G. This is linear, so their composition is linear. This is shift invariant, this is shift invariant, so their composition is shift invariant. So evidently, this composition is linear and shift invariant. Hence, as we proved, it is a convolution, which means that it must have a convolution rule, right? A spreading rule. The question then is, what is the spreading rule of the composed operation? And what did we learn in the first lecture? How do you find the spreading rule? The spreading rule equals the impulse response. So if we found the impulse response of this, that would be the same as the spreading rule of this. And so we put in an impulse signal and then find the impulse response, but we don't know the spreading rule. So how do we do this? You do this here, which means you put in an impulse and see what comes out, and the same thing must come out here because these two are supposed to be equal. If you put in the impulse here, what will come out here? Impulse response equals the spreading rule. So obviously f itself will come out here, right? F of 0, f of 1, f of minus 1, and so forth. And if f is what goes in here, what comes out here? What comes out here has to be f convolved by the spreading rule g, which means what comes out here is f star g. Isn't that brilliant? What we just proved is that if you cascade two convolutions, if you compose two convolutions, you get a convolution whose spreading rule equals the convolution of the two individual spreading rules. Okay. Now, if some signal X went in, not necessarily an impulse signal, some signal X went in, what will come out here? It will be x star f, right? That's our notation. And if x star f went in, what will come out here? That convolved by the rule G, right? But the same thing has to happen if I put in x here. But what comes out? The spreading rule here has the numbers f star g in it, right? This impulse response is this impulse response, which means it is the spreading rule. Now, if I put in the same signal x here, what comes out is x convolved with the spreading rule f star g. Look at this. X star f star g equals x star f star g. What shall we call this? We will call this the associative, yes, associative property of convolution. Write that down. So what we have seen in today's lecture is why linearity is important, why shift invariance is important, why anything that is linear and shift invariant is a convolution, and hence studying convolutions is important. Hopefully I have convinced you by now that studying convolutions is a good use of time for studying almost anything. And we went on to see how linear functions get composed, how that leads to this rule that we have studied called matrix multiplication, where that comes from, and we saw how to compose finally convolutions, and the fact that composed convolutions give convolutions, and their spreading rule is the convolution of the two individual spreading rules. We'll continue to discuss convolutions and their mathematical implications and their importance and their applications next time. Thank you very much.